Okay, so a beautiful good evening, ladies and gentlemen, or good afternoon. And I think very few people are joining us from a time zone where it is still morning. Thank you so much for joining us here, there, at the Azrieli Institute of Israel Studies for this very special engagement when we will be talking about reaching for the stars, Israel and the search for exoplanets, a conversation with Professor Shay Zucker and Colin Price. My name is Csaba Nikolenyi. I'm professor of political science and director of the Azrieli Institute of Israel Studies. And there's no doubt many of you who are joining us today remember and know this is a very special year for the Institute as we are marking the completion of the first decade since we started and since we opened our doors on the campus of Concordia University. What a delight that we are able to breach and bring an increasingly broader range of Israel studies to you and to our classrooms, to our campus. This evening is a very important example of this, because in collaboration with the Canadian Friends of Tel Aviv University, the Montreal chapter in particular, that is represented here today also by Sharon Frankel, the Chief Executive Officer of the Montreal chapter, we have brought to you a number of very important events already that showcase and explain the importance of Israel's scientific advances with particular attention to issues of sustainability and today the importance of astronomical research. Our two guests, as I mentioned, are Professor Shay Zucker and Professor Colin Price. Professor Zucker is a scholar of physics and astronomy. He received his PhD in 2002 from Tel Aviv University. He studies mainly binary stars and extrasolar planets. However, as he mentions on his biographical site, sometimes he also branches into studying other astronomical phenomena, starting from asteroids in the solar system through stars that are orbiting the center of the Milky Way galaxy, and even quasars. Now, Professor Zucker in 2004 was a postdoctoral fellow at the Observatory of Geneva, in Geneva, where he worked with the Nobel laureate Michael Mayer. And I do want to mention also that Professor Zucker also worked in the framework of another postdoctoral fellowship in the Weizmann Institute of Science, where he led a team from the institute itself and also worked from the Max Planck Institute in Germany. And that team also included another Nobel laureate, Reinhard Genzel. Professor Zucker has a mind-boggling number of 103 publications, and I'm sure that number already understates the current record of publications that he has under his belt. But just the ones that I saw on his website, 103 scientific publications. So what a treat that we are able to have you with us today, Shay, if you permit me to call you informally. And of course, our second distinguished guest, Professor Colin Price. Those of you who have been following our events, our seminars, will remember Professor Price from a very well-received discussion that we had about issues of sustainability earlier in the fall semester. My spies are telling me that today, Colin, you're also celebrating your birthday. So I would like to wish you a Yom Huledet Sameach on behalf of all of us in the family of Israel Studies and of course, the Azrieli Institute of Israel Studies. Professor Colin Price is an atmospheric scientist in the School of Geosciences at Tel Aviv University, and he's also the head of the Porter School of Environmental Studies. Professor Price's main field of research relates to global lightning activity and the connections between lightning activity and the Earth's climate. Those of you who want to treat yourselves to a fascinating and understandable, even to a political scientist, presentation about the relationship between pandemics and global warming, I would like to refer you to this fantastic YouTube clip on the YouTube channel of Tel Aviv University, where Professor Price explains the relationship between the two. So if you want to know just how closely connected the temperature of the planet and the temperature of the human being are connected, please refer to this fascinating YouTube clip. Even if you don't have a background in environmental sciences, atmospheric sciences, environmental studies, you will understand and appreciate the significance thereof. This event would not have been possible without the collaboration and the dedicated support of Mr. Sharon Frankel and his team at the Montreal chapter of the Canadian Friends of Tel Aviv University. So once again, Sharon, thank you so much for working with us. Thank you so much for being with us. And I would like to thank the two speakers, the two guests, for their willingness to allow us to record this event so that even those members of our community who are unable to be here with us or who will be joining us later on from the comfort of their home can pick up the conversation and learn from the wisdom that you are about to share with them. So without further ado, let me turn, if not the floor, but certainly the screen over to Shay. Shay, take as long as you need, 30, 40 minutes, it's entirely up to you, to tell us about exoplanets and the state of Israeli research in that realm. And then Colin and I, if I understand the format correctly, are going to be jointly managing the questions that some of which have already been sent to us in advance, and we'll be diligently collecting the questions also that are coming in the chat box. So Shay, the microphone and the screen is all yours.
Thank you. Thank you for this very heartwarming presentation. It was a pleasure to hear. Let me just, I need to share the screen, and you need to allow me to do it.
Absolutely. It's all yours.
So, the main topic of my talk is simply teaching you the basic concepts of exoplanets or extrasolar planets. So that's the main topic, and at the end, I'll try to shed some light on what's been going on in Israel in this field. Before I start, just a minute, before I start, I need to make sure that we all know what we're talking about and to do a little recap of the basic concepts in astronomy so that we can use the right terms. First of all, the very basic concept when we talk about objects, celestial objects, objects that we see in the sky, is the simplest object, which is a star. We see lots of stars, all the sky is full with the stars, but what stars are actually, a star is, the way we know it, and we have lots of evidence for that, is a ball of gas, very hot, emitting energy constantly, energy meaning light and heat, radiation, and it's been doing this for millions or billions of years. The very familiar, the most familiar star that we know of is, of course, our star, the sun. The sun is our star. A planet, I need to explain why I do this like that, because in Hebrew, when I give this similar talk to a Hebrew-speaking audience, in Hebrew, there's some confusion between the two terms, a star and the planet. They're like two types of the same object, and it's not the case. They are very different. When I'm speaking to an English-speaking audience, so maybe it's a little bit redundant, but still we have to make sure that we know what we're talking about. So a planet is a much smaller and colder ball, not necessarily of gas. It may be also solid. It usually orbits a star, similar to the way we orbit the sun. We, as the creatures that live on our planet, which is, of course, Earth. So Earth is a planet, the sun is a star, and we also know about the very famous planets, Jupiter, Saturn, Mars, Venus, All those are very familiar objects, planets that we know of since we were children. Now, when we're speaking about those planets, we usually have in our mind the concept of the solar system, the planets that orbit the sun. Of course, what we see here now is not, the objects are not to scale. We see here that Jupiter looks larger than the sun. That's not the case, and we see those small trails, colorful trails, they are not there. But that gives us an idea of what is the solar system, the sun, together with 8 planets that orbit it. So we have this third concept, the solar system, which comprises the sun, 8 planets, and actually there are many other smaller, much smaller bodies like comets, asteroids. Pluto is now considered something that is called Kuiper Belt object because it's very small. We also have a very small microscopic dust. So the object that we call the solar system is actually quite complex. But broadly speaking, or in general terms, it includes mainly the sun and the 8 planets that are orbiting it. Now, sometimes people confuse between the solar system and another concept because they have a different, very general shape, like a disk shape, in our mind at least, which is the concept of a galaxy. A galaxy is a system of hundreds of billions of stars, every star like our own sun. And they are arranged, it depends on the circumstances, but usually most of the galaxies seem like our own, and they have this disk-like structure. And we can see here other examples. Those are actual galaxies that were, whose photographs were taken by telescopes. So we see each one of those is a system of hundreds of billions of stars. So the fourth concept in this very short recap of the fundamental concepts of astronomy, a galaxy, a system of hundreds of billions of stars, and our galaxy, the galaxy that we reside in, is called the Milky Way. The reason is that if we go to a very dark place, we usually will see this band of light in the sky, and it got the name thousands of years ago. I think it was already the Greeks that gave it the name the Milky Way. So these are the 4 very basic concepts, that just to make sure that we know what we're talking about. Now, the main topic of this talk is exoplanets, or extrasolar planets, meaning planets that don't orbit the sun, but they are orbiting other stars than the sun, in the same way that we orbit the sun. Now, why is this such a challenge? Let's suppose for a moment, let's imagine we take a typical star, like the sun, we put it in space, and we attach to it, we put in orbit around it a typical giant planet, something like Jupiter. Now, we also need to have in this configuration an astronomer that observes them. And the question is, how easy would it be for the astronomer to say that actually there is a planet there? Now, why is this challenging? Because a typical distance between the star and the planet, like the sun and Jupiter, is a few million times smaller than their distance to Earth, to the observer. So this is the distance in the green arrow, the distance between the star and the planet. This is the distance between the star and the astronomer. And we see that we said that the ratio between those 2 distances is a few million times. So for us, they seem very close together. It's very difficult to resolve them, to tell them apart. Now, not only that, but the light that is reflected by a typical giant planet because I'm saying reflected because there is no process of producing energy like there is in a star, so it only reflects the light from the star. The typical amount of light that is reflected by a giant planet is a few billion times less than the light emitted by the star. So this adds to the challenge, because they seem very close by to us. This adds to the challenge, the fact that the planet is so faint. So this challenge made it very difficult to detect planets, and we had to resort to indirect means to detect them. Now, currently, the main technique, the main method that we use to detect planets is what we call planetary transits. It's a very simple idea. The idea is that there is a chance that while the planet is orbiting the star, during its orbit, it periodically hides part of the star. It crosses our line of sight to the star. Let's see what I mean. If we were to look at the orbit of the planet like this, we see it face on, then there's no hiding. The planet doesn't hide any part of the stellar disk, what we call it, the star. However, if the configuration, the geometrical configuration is like that, simply that the orbit is arranged in space in this way, then during this period, this interval of time that it crosses here, then it hides part of the star. Let's see it more clearly in this small movie. We see a star, a simulated star, and we measure the amount of light that we collect, that we simply measure the light that we see in our telescope, in our instruments. Now, we monitor the light in time, and then what we see here, the planet starts to hide part of the star, and then we see a drop in the amount of light that we measure. This is in the plot down there. So this happens periodically. So what we see is that since we are not really able to see the planet, we can only measure the amount of light. We see a minute drop in the light that lasts typically for a few hours. And we see that it happens periodically because the planet orbits the star in a periodic fashion. So detecting such periodic dimming of the light from the star is a telltale sign that there is a planet there. It can be other things as well. So once we see this periodic dimming of the star, we have to make sure, we have to do additional observations to check for several other things to make sure that the cause of those dimmings is a planet. One problem with this detection is that what we see here is that there is an object that causes this periodic dimming. We don't know it's a planet. It may be that it's actually a very small star. It may be that it's a black hole, if you want. There are many options. In order to tell apart a planet from another object that might cause this periodic dimming, we have to be able to weigh it, to say what is its weight, or the way we say it, its mass. We have to be able to measure the mass. The way we do it is by using what we call the Doppler effect. Suppose we have an object that is emitting waves, some kind of waves. It can be a boat on a lake, and there's someone that is tapping the water and inducing waves in the water. It may be a vehicle that is making some sound, like a car or a motorcycle, and it can be a source of light. In any case, it's a source of waves. Now, suppose that this source of waves is moving to the right. Then what happens is that if we are standing here, the observer or the listener, we see the waves sort of squeezed because of this. It's not exactly what I say, but it's easy to imagine intuitively what happens here. They are squeezed by the motion of the object, of the source. If we stand behind, we see the waves spread. The time that passes between each peak of the wave is longer than the way someone that is sitting on the object sees it. The easiest way to imagine this is by thinking that there is a motorcycle that is making a sound, and usually we are used to hearing this sound. Our brain immediately tells us that in the beginning it was moving towards us, and then afterwards, when it passed us, it started to moving away from us. And we heard the difference in the pitch, because in the pitch of the sound. The reason is this Doppler effect, this squeezing or spreading that depends on the velocity in which the object moves towards us or away from us. Let's hear it again to imagine this. Now, how is this related to weighing planets? We all know this phenomenon that we call rainbow. The reason to the rainbow is the fact that the light from the sun includes all kinds of frequencies, and in rainy days, depending on the arrangement of on the geometry, there's a possibility that the light waves from the sun are refracted or broken in the atmosphere, interact with the water, and we see the light separated to its components, to its ingredients, to the frequencies that comprise it. And the way our eyes interpret light frequencies is by assigning to them colors. That's what we do biologically in our brain and in our eyes. Now, when we use dedicated instruments to take the light of stars and separate the various frequencies, we see this, we get this picture where we see what we call spectra in plural, spectrum in singular. We see this like a rainbow-like image. We see on one side the red light, which is the lowest frequencies of light, and on the other side we see the blue light, which is the highest frequencies of light. And we also see some black stripes here. This is what we call black lines. We call them absorption lines. It relates to various processes that take place in the star atmosphere. And an experienced astronomer would tell you that they see here a progression of temperature. Each one of those spectra belongs to another star. Every star, there is a specific image here, and we have to remember that what we see here relates to the frequency. The right-hand side is the low frequencies, the left-hand side is the high frequencies. Now, suppose we take a spectrum of a star with all those absorption lines, and let's assume that the star is receding away from us, moving in a velocity away from us. Because of the Doppler effect, what we will see is that all this image, all this spectrum, as we called it, will be shifted towards the red because of the fact that all the frequencies will seem like they are lower frequencies than the star emitted them. So we'll see all this picture here shifted to the right. We call it redshift because it is shifted to the red right-hand side. On the other hand, if it approaches us, then we'll see this image shifted to the left, to the blue side. So we have this terminology of redshift or blue shift. Now, this means that by taking the spectrum of the sun, we are able to measure, of the star, sorry, we are able that is ice skating. When we have this whirling, or how would I call it? Whirling, yeah, probably. We see that in order for the female to be able to make this very large round, like orbiting the guy also has to do a small circle in itself. The same way happens with a planet and the star. It's not only that the planet orbits the star also moves. There are very fundamental reasons, physical reasons for this, but I think that this cartoon of ice skating is demonstrating intuitively what happens. So in case we have a planet orbiting a star, there are times where the planet is receding away from us, we observe from here. And in those times, the star is doing a mirror motion, like the dancers, like the ice skaters here. And then the light that the star is emitting will be blue shifted because it moves towards us. Now, on other times, the planet is approaching us, but we don't see it. We see instead the star receding away, and then the stellar light will be red shifted. So what we do is that we go to a telescope and we take, we direct the telescope towards the star that we examine. The stellar light goes to this instrument that we call a spectrograph. It sits in a different room. It's cryogenically stabilized. And then, we get the spectrum and we repeat it several times until we can say that we see the motion of the star caused by the planet. And by analyzing it, we can determine the mass of the planet. Now, we explained how we detect planets, the main method to detect planets. We explained how we make sure they are planets by weighing them, measure their masses. And the question now is, what else? Only detecting them is not enough to make science, to do science. So we have to be able to study many other aspects of the planet. So one example is that we are able to tell a few things about the planet atmosphere. Imagine that we have a planet that is transiting the star, occulting or hiding part of the star. What we didn't have earlier in our image is the fact that this planet has an atmosphere. And during the time that it hides part of the star, some of the light rays, some of the light from the star actually passes through the planet atmosphere. And we are able also to take the spectrum of the star and see how it changes before and after the event of the hiding. And then we can tell apart the effect of the planet atmosphere on the light. And then we are able to say a few things about the physics and the chemistry of the atmosphere. So when I did my PhD 20 years ago, this was considered science fiction. Okay, we detect planets. I did it in my PhD. But be able to say specific things about the composition of the planet atmosphere, this seemed to be out of reach. Nowadays, we do it. Not regularly yet, but it's still very difficult, but we are able to do it. So these are very exciting times. When I started to mention what I did 20 years ago, I have to mention that to give a feeling about the timeline. The first exoplanet detected was, was detected in 1995. It was detected by Michel Maillot, who was my postdoc supervisor in the University of Geneva, and his then PhD student, Didier Queloz. Together, they did it on the Swiss telescope in Chile. and they actually were awarded the Nobel Prize about, depending how you count it, 2 or 3 years ago. So they really changed, they started a new discipline within astronomy, which is the discipline of exoplanets. Currently, this was the first exoplanet, and during my PhD, I think when I started my PhD, it was about the same year, 1995, and I started it, there were, no, 1996, there were 9 planets already. When I finished it, there were about 100 exoplanets known. Currently, we know about 5,000 confirmed exoplanets. So what can we say about them? What is the planet demographics? We see that there are many giant planets like Jupiter. We see also very small planets, what we call terrestrial planets that are like Earth. I say see, but we don't see them. We measure their effect. Either they are hiding part of the star, or we measure the radial, the Doppler shift that they induce on the star. But we are able to say things about their size and their mass. So we see giant planets, we see small Earth-like planets. There was already in the first planet it was detected. It was a huge surprise because what Michel Mayor and Didier Queloz detected was a giant planet like Jupiter, but extremely close to its host star. And then there was another one and another one. And nowadays we know it's a very common phenomenon of a giant planet that is very close to its star. We don't have things like that in our solar system. The giant planets, until the 70s, until the 90s actually, the theories that explain how planetary systems form assume that, like the solar system, giant planets are far away from the star, and they explained why it happens. Eventually, the first planet that was detected was extremely close to its star. We had to revise our theories to find out what went wrong in our theories. So that was, we call them, those planets, hot Jupiters, because they are like Jupiter's giant, and they are very close to their stars, so they are heated by the stellar light and energy that it emits. We see planets in systems of binary stars. That's very reminiscent of what we see in Star Wars, on Tatooine. Tatooine is orbiting a system of a binary star, and we see 2 suns here. So we have, no, this happens not only in movies. We see there are quite a few cases where we actually detected planetary systems, a system of a star that is orbited by several planets, like the solar system. Okay, now the million-dollar questions. Question, what about life? What about life? Obviously, we don't expect life to form, to be created or to be formed or exist on stars that are extremely hot, thousands and even tens of thousands of degrees in stellar atmospheres. We expect life, if it exists out there, to exist on planets. In order for life to exist, the way we understand it, we need to have a fluid, liquid water. So when we have a star, we can define a range of distances from the star where liquid water can exist. We don't know if it exists, but it can exist when we take into account the energy from the star. It has to be in what we call the Goldilocks zone. It has to be not cold and not too hot. We don't, if we have freezing ice instead of liquid water, then we don't, we have theories explaining what are the most suitable minimal conditions for life. And if the temperatures are freezing, it's not hospitable to life. If they are boiling hot, of course they are not. So it's like we call this, there are many astronomers that call this region of either the habitable zone or the Goldilocks zone. The current challenge is that in order for liquid water to exist, the planet has to be a terrestrial planet, meaning solid. So it can't be a giant planet, it has to be small, and it has to be far enough for the water not to boil. So that makes it very difficult to detect. If it's far away from the star and it's very cold, it makes it very difficult to detect for detection. So the current challenge is to detect more and more habitable planets, terrestrial planets in the Goldilocks zone. Now, I want to review some of the space missions that were key players in this game of exoplanets. The first one is until recently, or still is, the most important one, which is Kepler, the Kepler Space Telescope. It was launched in 2009 and it operated for about a decade. And during its time, it detected about close to 3,000 planets. So I said that we know of about 5,000 planets. And so you can understand that most of them were detected by Kepler. So Kepler made a revolution in the field. Currently, the space mission that is in operation now, and it detects more and more planets, is TESS, acronym for Transiting Exoplanet Survey Space Mission, Survey Satellite, It's launched 3 years ago, and so far it detected about 200 planets that were already confirmed, and there are close to 5,000 planets detected by TESS, planet candidates that are waiting for confirmation. A lot of work. The main difference between TESS and Kepler is that Kepler focused on one region of the sky, whereas TESS is a survey satellite and it scans the whole sky. Probably you all followed the launch of the James Webb Space Telescope, or Webb Space Telescope, or JWST every time the common acronym or the common name changes. The James Webb Space Telescope was launched a month ago. It's a joint project of NASA, ESA, the European Space Agency, and the Canadian Space Agency. And it performs infrared observations, not observations in what we call visible light, but in the infrared. Infrared is very important because most of the interesting things that can happen in a exoplanet or in planetary atmospheres have the main pieces of information in this regime of electromagnetic radiation, infrared. So that's one of the main science goals of the James Webb Space Telescope, to be able to allow us to characterize exoplanet atmospheres, and in doing so, we hope it will allow us to search for signatures of life. Another space mission which is dear to me is Gaia. Gaia was launched in 2013 by the European Space Agency, and Gaia is in the process of completely revolutionizing all fields of astronomy. It has a very high resolution and also allows us to be able to pinpoint exactly where every celestial object is. However, Gaia was not meant for detecting exoplanets. So that's one thing that is not doing optimally. However, I took it upon myself to make sure that Gaia fulfills its potential to detect exoplanets, even if it's not optimal, but to make sure that we don't lose any piece of information. So recently we detected a few planets and we are now writing the paper about it. So even Gaia detected planets. Gaia is very important because it gives us very detailed characterization of stars. And when we want to be able to say what exactly happens on an exoplanet, we have to first say what are the features of the star, of the host star of this planet. Now, I promised that I will talk about the role of Israeli astronomers. Israeli astronomers from all the universities in Israel are involved in all those projects. But I still think that in Tel Aviv University, the group in Tel Aviv University has a unique role, because my PhD supervisor, Professor Tzvi Mazeh, was part of the team that worked together with Michel Mayor and an American astronomer during the first detections. And I think that in terms of detecting exoplanets, I think our group is the most important one in Israel, except maybe the Weizmann Institute. They also have a group that is starting to do some work in this. In other universities, people are doing more theory, trying to understand how those exoplanets formed, how they evolved, features of their orbits. But detecting exoplanets, I think Tel Aviv University is the leading university in this respect. Now, I want to tell you one specific contribution of Tel Aviv, which is a collaboration that we initiated between Gaia and TESS. I remind you, Gaia, I'm a member of its data analysis consortium. It was launched by the European Space Agency, and TESS, that is scanning the sky looking for transiting exoplanets. It's an American mission launched by NASA. And you can imagine that there is a strong competition between ESA and NASA. Gaia is maybe the flagship of the astronomical space missions of ESA. And TESS, I can't say it's the flagship because I think now the James Webb Space Telescope is the flagship, but it's not operating yet. And TESS is the flagship of astronomical space missions of NASA. Now, here comes Tel Aviv University in the junction. We initiated this collaboration because we found out a missing, a lacuna, something that was lacking in the ability of TESS that Gaia was able to contribute. What is it? Let's see, this is the sky, and it's a relatively high resolution image. The problem is that TESS, as it observes the sky, it does so with a very, let's say, very wide pixels. This is the pixels of the detector that is on TESS. And you see that the pixels are much larger than the images of the stars. On top of that, the image is on purpose blurred. It's not a bug, it's a feature, and they had a reason for doing this, but it's still a problem. Why is it a problem? Because if we observe a star here and the star shows a transit, meaning that we see this periodic dimming, we cannot say whether the star is the star that we saw earlier here, this star, or maybe it's this one or this one, and then it would be a much deeper transit, a dimming, a much more serious dimming, or maybe this one or this one. We can't say what it is. When they launched TESS, they said that that's going to be the case, and that's why they appointed a specific team to do follow-up observations from the ground at each what they called transit object of interest. When they see such a dimming, they started to follow it up from ground-based telescopes to say whether the transit actually happens on the target star or on one of its neighbors. And we said, we are accumulating data from TESS, and TESS has a superb resolution, even more than what we saw earlier. You see all those small blue squares. That's the way Gaia sees the sky. So we have within the consortium that analyzes Gaia data, we have all those measurements archived. As we analyze them, eventually we'll publish it, but they are waiting for analysis. And we said to the management of Gaia, listen, we can help the American with this information. So they have to devote time on ground-based telescope to do these high-resolution observations. We have it ready on our servers. We can simply tell them, tell us where you see the transits. We'll go to our archive and see whether we can tell them, listen, the transit that you see is not on this star, it's actually on one of those background stars. So it's not interesting. So that's how we initiated this collaboration. It was very difficult because the two systems, the two space missions and the two space agencies have their own rules for publication and for sharing information, and this was something that fell, it was an uncharted territory. How exactly are we going to share this information? So in 2018, there was a conference in Vienna, and I attended it. We were talking before the conference about this idea, and then I told Tzvi Maze, who was in Israel and I was in Austria, I told him, listen, I see in the room George Ricker, the principal investigator of TESS, and I see Timo Prushti and Anthony on the management, from the management of Gaia. They are both in the same room as I am. We can make them sit together in one table and negotiate this way of sharing the information. And he told me, don't do anything. He bought a plane ticket, and during the afternoon, he came to Vienna. And then we arranged this meeting, and we managed to do it. It took about 1 year of negotiation later before this started to work. But nowadays, what's happening is that we in Tel Aviv University have access to the Gaia archive. We get from TESS the alerts saying that we see what an apparent transiting planet in these coordinates. We go to the archive, we check this, and if we see that we have something important to tell them, something that would save them observation time, we have permission from Gaia to tell them about it. So this all takes place in Tel Aviv University. Because we initiated this, we had the machinery going for doing all those tests. Tzvi Maze, my former PhD supervisor, was a member of the TESS consortium. I was already a member of the Gaia consortium. So all the stars were arranged in a way that allowed us to make this happen. So, like you see, Tel Aviv University is located in a perfect position to contribute superbly to this exciting and growing discipline of extrasolar planets. So I think I'll stop here. Thank you very much.
Thank you so much. I mean, you made it fascinating and understandable to a political scientist. So I'm sure I speak for everyone around the table or in front of the computer screen, just to say how fascinating and absolutely brilliant this was. So thank you so very much. Colin, would you like to join in the conversation and maybe bring some of the questions, issues that you might?
Sure. So I'd also like to thank very much Shay. This is, I think, a mark of a great scientist is someone who can explain such a complicated topic in such a simple and down-to-earth way. It's extremely difficult to explain all these concepts and ideas. And I've heard Shay give a few lectures, but this was actually amazing hearing how he explains this to the public in such a down-to-earth way, in such a complicated topic. So thank you, Shay. So I have a few questions. The first one, as a scientist, so do you believe that life exists on other planets?
Well, you know, we had several centuries ago, we had the Copernican revolution that changed the way we see mankind and Earth. We are not the center of the world. We are not unique. So as a scientist, I can't imagine that there is no life out there. the question whether, they visited us or whether we are able to communicate with them, to detect them, I don't really know. I'm optimistic. I think that in our lifetime, or maybe even in the next in this decade, we will be able to say whether to detect life in space. Whether we will be able to detect intelligent life, that's a completely different story. But obviously, I can't believe that there's no intelligent life in space. So that's a short answer.
And what about extraterrestrial life in our solar system? Even though that's a lot closer to us, is the search exhausted already, or do you think we're just beginning to look for different types of life in our solar system?
Many people think that the search is exhausted because, we had the Viking spacecraft landing on Mars and they didn't find anything. And actually, that's not true, because the findings on Mars were never conclusive. We can't say we didn't detect life or remains of life on Mars. That's why NASA and other space agencies are still sending spacecrafts to Mars, because the search on Mars itself is not exhausted yet. In the recent decade or two, we found very interesting things on moons of Saturn and Jupiter that we never thought that they could host life, but actually we now know better that there may be under oceans under the ice that may be hospitable to life. We know that there is liquid water on some, or underneath the ice on some of Saturn and Jupiter moons, and we now understand that this may be the case on other icy worlds, even Pluto. So in any we can never say, or not we can never, but obviously the search is not exhausted, at least not now. So there are many more places to search for life in the solar system. We can't say that we exhausted the search. Then we have the search on other solar systems, planetary systems. That's a completely different story.
Okay, and one more question before I pass it back to you. I have a number of questions, but I'd like to let other people maybe ask questions. But you said we've now detected maybe 5,000 extra solar planets. Do you think that every star in the sky has planets around it, or are there stars no planets?
The question of the probability of a star to host planets is a topic of active research. We have to remember always that when we don't find planets around the star, it doesn't mean that there are no planets. It means that our methods of detecting planets, they have some false negative. Nowadays, the phrase false negative is very common. So there is a very high percentage of false negatives. It's like an antigen test. So we have, when we try to estimate the probability of having planets around the star, we have to take into account we have to account for the false negative probability in our search. So currently, when we do this very carefully, it seems that at least every star seems to have at least one terrestrial planet. That's amazing. So every star that we see in the sky has at least one terrestrial planet. Actually, giant planets are a little more rare, but they are also very common. So the phenomenon of having planets is extremely common. Most of the stars do have planets. It's actually very rare not to have a planet.
Yeah. And it's fascinating that this was only discovered 30 years ago or so, that before 30 years, nobody would have thought of planets outside around other stars. And now it's just common belief and common knowledge. Csaba, you want to ask any questions?
Yes, thank you very much, Colin. Shay, there are a number of beautifully written and worded compliments coming in to thank you for really bringing this tremendous knowledge and wisdom to our screens. What I would like to ask, and this is actually something that Rosa is raising from the audience, is whether you could tell us a little bit about the application or the applicability of exoplanets for our life on Earth. In other words, is knowing about exoplanets, is it purely science, which is great, or can the knowledge that we gain about them somehow be used for practical purposes, either for life on Earth, for how we organize our life on Earth, or for how we organize our future space exploration? So is there any additional benefit, or what is the additional benefit and applicability of this tremendous knowledge that you're building up about exoplanets?
The same question can be asked about any field in astronomy. When we talk about things that happens or take place hundreds of light years away, what is the applicability to our life? I want to mention something that is a little bit off topic. When people, around the 60s, the 1960s, there was an idea of an astronomer or a solar scientist to study the structure of the sun by taking images as the Earth orbits the sun, taking images in several angles, and building a three-dimensional image like a cut of the sun. About a year afterwards, the method that they developed was applied to invent the computerized tomography, the CT. We have like Earth moving, orbiting around the sun. We have the instrument of the CT orbiting the human body to get cross sections of the body. So that's the thing with basic science. We have no idea how it's going to evolve and contribute to our understanding of the world. In other fields of astronomy, we know that when we study, we get a better understanding of the very fundamental physics. When we study black holes, we understand more correctly the issue of the topic of gravitation. In terms of exoplanets, I think it's still too young. This discipline of exoplanets is still too young to be able to say how it's going to change our lives. But I think that it is essentially maybe the strongest influence is the fact that it's a kind of a second or third, maybe Copernican revolution, to understand that the solar system is not unique, or it's not one of a kind. In many respects, we see that the solar system is unique because its structure is very different from the configurations that we see on other planetary systems. We will be able, when we analyze the data that we are accumulating now, we will be able to understand more thoroughly the way the solar system formed. And that may have implications. We're still not there. We still haven't processed all the new information. But I think that understanding how the solar system formed means that we understand how Earth formed, and who knows what new knowledge it will give us. I can't answer it more than that.
Of course. No, that's wonderful and very honest. Thank you, Shay. We have a question from Irving Epstein, and here is the question. By looking at Mars, which may have had water and maybe life, should we be looking for the reason life is no more? Can we learn from this to not end up like Mars?
Of course. I think that when we detect life, or when we detect life that had existed in the past, we should be able also at some point to understand why it doesn't exist anymore, assuming that it doesn't exist anymore. And of course, that will have enormous implications on our understanding of not only how life can form, but also how they can be destroyed. How can, we have Colin here that he's an expert on sustainability. the issue of sustainability will probably benefit, our understanding of sustainability will probably benefit enormously from what we see on other planets once we detect planets that had life. It will have, yes, it will have a tremendous implications. Since we are not there yet, I can't know what exactly we know.
Yeah. So just to ask one last question, because we did tell our guests, we did ask for their time and for availability for an hour. And of course, it is getting late, much later in Israel than it is getting in Montreal. But I would like to ask you, Shay, and maybe both of you, or either of you could comment on this, is to push a bit forward the notion of where Israel is located in this fascinating research about what you call the second and third Copernican revolution. And thank you for situating the role of the science and the scholarship that is being done at Tel Aviv University in particular. So where is Israeli scholarship and Israeli astronomy located in this revolution? In other words, how important is exoplanet research today in Israeli, at the Israeli departments? I mean, you mentioned that Tel Aviv University, Weizmann Institute, those are the two prime areas, the prime institutions where exoplanet observation and analysis is done. Do you have a next generation of young doctoral students who are interested, like you were back at the time, working on this? Or is it, in other words, is this a field that's growing? Or is this a field that's very much still limited to a couple of professors, researchers such as yourselves, very much still waiting to gain the kind of traction that you would like? Or is it already a growth industry in the Israeli astrophysics and astronomical community?
First of all, in astronomy in general, Israel enjoys a very good reputation because I mean, I can see this when you do what we call bibliometrics. You see the publications from Israeli astronomers. You see we compete for observation time, and Israeli scientists always have very good statistics in winning observation time. Now, specifically for exoplanets, I think that Tel Aviv University is still #1 in this area. And like I said, Weizmann Institute is growing because they are about to launch a satellite that will contribute to various aspects, but also to exoplanets. And they are also, they hired recently an instrumentalist that is building a spectrograph that will be used for exoplanets. So yes, I think that the field, you can say that, especially in Tel Aviv and in Tel Aviv University and in Weizmann, the field is growing, maybe exponentially, I'm not sure, but it is growing. But you can. I don't want to be a chauvinist, an exoplanet chauvinist, because the astronomy in general is growing, not only exoplanets. But yes, I still think that because of myself and because of my former PhD supervisor, Tzvi Maze, I think that we still enjoy a unique position in this. We are the most senior exoplanetologists in Israel. So yes, it's still, it is growing, and we have students, of course. Yes, it's alive and kicking, the exoplanets.
That's wonderful.
I'll make one comment about space in general in Israel. That I mean, the Israeli space industry is one of the members of the World Club, which, when there was only China and US and Russia and a few others who could actually do it all, Israel joined that club, I think, at #7, where we could build, launch, and launch satellites and get the data all by ourselves, not relying on other countries. And still today, Israel is a leader in space technologies and launching satellites, whether they're communication satellites or others. And now, linked to the Canadian friends, what we're doing now is we also have entered the new age, what we call new space, which is on these very small CubeSats or nano-satellites, which students can build. Even high school students in Israel just launched a few weeks ago 8 satellites from 8 high schools around Israel. And so in the new space arena, which is also a growing field, Israel is really becoming one of the key players there, and Tel Aviv University as well is part of that.
Colin, I cannot thank you enough for mentioning that. In fact, in our publicity to advertise this conversation with you and Shay, we did share a link to that news item that circulated about the launch of these 8 student-built constructed satellites. It's truly, truly just remarkable. So thank you. Shay and Colin, you've been wonderful. Thank you so much for bringing this fascinating knowledge and insight and universe to our computer screens. I have to tell you that never again will I watch a figure skating competition the way I did before, and never again will I be looking at the star and not thinking about the male figure skater and thinking, okay, what is the star doing now? This was just brilliant, and I will make sure to share with you any other questions and comments that we will be receiving after this talk, and of course in response to the recording that we will make available to those who could not join us today. And so thank you. I would also like to once again and publicly thank Sharon Frankel and his team at the Montreal chapter of the Canadian Friends of Tel Aviv University, who are doing so much to support this tremendous explosion of research and knowledge in space research that Colin has explained. So thank you, Sharon, and thank you for your collaboration in helping us to breach into Israeli scientific knowledge and the scientific community during this semester and the previous one. And of course, my thanks go also out to our social media coordinator, Lisa Komlos, who is working diligently in the background to make sure that this event in real time technologically is implemented with no hiccups, and that all the advertising and the publicity goes out to a wide range of constituencies and stakeholders. So thank you, Lisa, for everything that you do. Ladies and gentlemen, please join us again at our upcoming event. We will have another seminar later on this week on January 27th on Thursday. And you can find out information about this important seminar on our website or in our recently circulated newsletter. Shay, Colin, and Sharon, once again, thank you so much for this fascinating evening. Goodbye, everyone.
Thank you. You're welcome.
Stay healthy.
Thank you.
Good evening.
Bye. Thank you.
Bye.